Okay, couple of remarks. I posted the grades online for the second one. So let me know if you have any questions. If you want to go through any of the problems, we can do that. In addition, I asked you guys a question what was difficult for us. So if you have any feedback on that, just let me know. For the exam, what I'll do is do the same setup actually, at least for the first one. It will be again a 48-hour exam. It will be again posted on Sunday 9 a.m. due on Tuesday 9 a.m. Okay? So in that case, anyone that wants to have a weekend off, can have a weekend off, you can do it on Monday to Tuesday. Anyone that's basically wanna just do it on the weekend, have full time for it, you can do it basically on Sunday. It should not take more than a couple of hours to do, to be honest. It's gonna be approximately 6 questions, I would say, for target shear, bending, torsion. We'll talk about definitely multi-section. We will definitely talk about idealization and the next topics that we discuss after this. So the date I haven't picked yet, but I'm gonna guess. So let's have a quick look at the calendar.
So it will be online.
Sorry?
So it will be online. So
Yeah, it will be online. So I think the last day of class is the fifth, right? And I think so. It's gonna probably be yeah, the second to third. Let me just pull up the aerospace course. I'm 100% sure which dates I'm talking about. Because I'm on the syllabus. So yeah, the syllabus is on the screen. For those online, it's not on your screen, but it's on the screen in the classroom. So here we have, hold on. Okay, so we had the final exam on the 4th, and it was an in-class. Read the day 27th. Okay. So based on that, and I want to do 2 exams, we're gonna actually have it earlier than I expected. Yeah, we'll have it then. Yeah, I'll do the 25th to the 27th. So that will be next week. Will be the first final exam, and the second final exam will be the 2nd to the 4th. Again, 48 hours, both of them. So what we will do is this. I'll focus this week on and next week on the last topic. That will probably be section shear flows, like in panels, with a cutout in it. I think that would be the most crucial part, or most advantageous. And for today's lecture, we'll basically go into what we already discussed and finalized as multi-section, shear flow problems. I think this problem is example 23 point something. You have basically 2 cells and there's a shear force applying to it. And we're gonna solve that for today. Yeah. So the exam dates again, they will start next weekend, the 25th, 9 a.m. till the 27th, 9 a.m. And then, which I will basically cancel next, the 27th lecture, because then I will grade it. And what we'll do is then the lecture of the 29th, I'll just go through the exam, problems that I think was made, people made errors on. And then the next exam, your reset, your second exam, will be from the 2nd to the 4th. And that will give you 2 opportunities to do exams.
So just to clarify, the first final exam, if we're satisfied with whatever grade that is.
Yeah, you can skip the second. Just let me know per email or basically you don't do it. Yeah. Because, yeah, but I will ask people for confirmations if they are intending to do it or not to do it, so I know a bit of an idea how many people will do it.
And then if you give both of these, you could
Yeah, you could do that. But most of the time, what I noticed, like, there's one guy who has improved on it. I've been doing this for now 6 times. Yeah, 5, 6 times. And there's only one guy that improved on it. Most of the time, people think they're going to improve on it. And they will focus on one topic, what they did wrong. And then they let, because it's still, again, a new exam. So the same topics may appear, different topics may appear, etc. Yes?
I don't think there's a lecture on the 29th.
There is?
There is not.
There's no lecture scheduled at all. Then we just, I can do an online lecture. I can choose to have this room. So if you guys want to be present, I can do it. But what I'll do is just what my idea was: grade the exam, show the grades, and then go through what people did wrong. So if people those who wanna improve, they know what they did wrong, and they can improve upon that. Okay. So I think the missing a couple of lectures. So we have to trim it down a bit, but that's okay. I think the main topics we got through it, and then we focus Thursday and Tuesday and Thursday next week on the last topic. That should be enough for that. Okay. With that said, we're gonna focus on today's lecture. It's multi-section shear flow problem, and we have booms as well. So we have two cells, cell 1, cell 2, and the following is given. 1, 2, 3. 1, 2, 4, 5, and 6. And we have an idealized cross section, 2 cells, thin walled. We have a shear force acting at Sy equal to 4,400 or 4,500 Newton. We have the same shear modulus everywhere. So the shear modulus is just G, shear mod, G. And then we have a table with a bunch of information that gives us, so wall, 1,6, 2, 5, 3, 4, 2, 5, 3, 4, so 1, 6, 2, 5, 3, 4, okay. So 1, 2, 5, 6, then 2, 3, 4, or 5, 4. You see? Yeah. So 2, 4. Then we have given the length. 2, 5, 4. 4, 5, 2, 2. 4, 5, 2, 4, 2, 6, 4, 7. And then we have also the thickness given for each wall.
I think it's 775.
You're correct. 1625. 2. Right? And then we have the boom areas. Say B16, 2 and 5, 3 and 4. And those are given as 1290 and 36, 1290, 1936, 945, 645. Confused. So a bunch of data given. Basically all the data to solve this problem. Since this is a multi-section and it's closed section, so the procedure It's basically similar to what we had in the past, but then we just repeat it twice. So step 1, make a cut. Step 2, solve the open section, QB. Step 3, find QS0. QS0 is the correction shear flow. Because we have a multi-section, that means we have 2 correction shear flows, 1 and 1, and 1 and 2. So where do you want to make a cut? Again, we want to make it at the location that's it's going to be convenient to us, and that based on symmetry we can reduce the computations. So in this case we know the shear force in the vertical section, we know it's symmetric, so we know also we have a boom problem, so the shear flow only changes when we have crossing a boom. Yes?
So the area 1 and area 2 are symmetric, because it doesn't look like that in the textbook problem.
No, they're not symmetric.
Okay, so it's symmetric about the x-axis then?
It's symmetric around the x-axis, yeah.
Okay,
So the plane of symmetry lays is on this side.
gotcha.
So it's definitely not symmetric in the y section. Actually. Much easier if I have it here. Okay. Yeah. No. Alright, we have also a couple of more dimensions given. This length and this vertical or horizontal length. 635 and 763, 635. Okay, perfect. So the idea is now, okay, let's make the cut and see where we can determine the best location. So because we have a plane of symmetry, so we know that the shear flow in 5-6 should be equal to 1-2, 3-4 equal to, or 2-3 equal to 4-5. So if we make our first cut at these 2 locations, because we have an idealized section and we know that the shear flow only changes when we pass a boom, that means at this location, 1-2, the open shear flow is 0, and that means at 2-3, the open shear flow is 0 as well. By default means symmetry that 5-6 and or 6-5 and 4-5 is 0 as well. So in this case, we only have to calculate 1-6, 2-5, and 3-4. Yes?
If we only made 1 cut,
Then you cannot solve it.
okay, so why do we have to make 2 cuts again?
You basically have 2 closed sections.
Oh, okay.
So you have to make 2 cuts.
So had there not been a connector from 2 to 5, we would have had to only make 1?
Yeah.
Okay,
Then we have 1 closed section.
gotcha.
So yeah, the number of cuts must always equal to the number of sections as well. So, so we know that. So we already know that basically this is 0 as well, and this is 0 as well. And basically those 2 will basically determined based on the correction shear flows. So with that given, we can start off with also identifying which equation we have to use. So what we also know is we have symmetry and x-axis, or on the x-axis. So we can reduce our problem. So we get our correction shear flow, or the shear flow equation. This is the correction shear flow, and this is the open shear flow problem. It's a bit hard. Let's see if the blue one is better. Nope, it's definitely better. Yeah. Okay, so I also know that. So what we also know is that moment of inertia, of course, since we have an open boom area, will be equal to by squared. So we can start off with that. So because it's symmetry, we can easily just multiply everything by a factor of 2 and just look at the top half. So we've got 2 times, let's start with, let's start with 1 actually. Boom, 1, that's 1290. The y area, the y distance is basically 1/6 over 2, so that's 254 over 2, so 125, 127 squared, plus boom area 2 is 1936, multiplied by 25 over 2, that's, let me double check that number, that's 406, not 405. So this is 406. That's 203. Square root. Squared. And this last one is number 3. That's 645. Boom area multiplied by 334 over 2. That's 202. So it becomes 101. And the 2 is there because of symmetry.
Is it 1936 or 1436?
It's 1936. Yeah, 1936. That gives you a total of 214.3 millimeters to the power 4. Oh, wait. 10 to the power 6 to the power 4. 10 to the power 6 millimeters to the power 4. And again, what we did in the past is we use this as just a number. It's a bit easier to calculate. So SY or IXX. So we do the same thing. So we realize that this is nothing else than minus 44,500 over 214.3 10 to the power 6. So if we do that, plug that in, we get 208 10 to the minus 4. So minus 2.08 10 to the minus 4, and then by b times y. I'm just gonna ignore the subscripts for now, plus qs0. That's the correction shear flow.
So you said that was negative 208?
Yeah, negative 208 10 to the minus 4. So it's often sometimes it's sometimes it's easier to keep it as SY, and sometimes, especially in shear flows, it's a bit easier to keep it as calculate the number and use that, continue using that number. Okay, so yeah, so we made our cuts, so we know that's 0. So now we can calculate basically the shear flow, and it doesn't matter which way we go. So if we can choose to make the cut in 1, 2, and then go basically up, or we can make a cut in 4, 5, and then go down. For now, let's just stick to these cuts. So we're going to go up. We're going to go from 3 to 4. We're going to go from 2 to 5, and we're going to go from 1 to 6. So there's our open shear flows, open sections. So we have QB 16, negative 2.08, 10 to the minus 4, multiplied by this boom area 1, so that's 1290. 1290 multiplied by the y distance from the centroidal axis. Again, we don't know centroidal lie in the middle. No, actually, it doesn't lie in the middle. But we don't know where it lies on the x-axis, but it's not crucial to solving this problem because we know it lays on the x-axis. So we only need to interested in this distance towards the y-axis. So and that was equal to what we already calculated here, 127. But in this case, the sign of it is important because it's not squared, so the sign becomes important. So we have multiplied by minus 127. If we do that correctly, we get 32.8. Newton.
On our exam, is it likely that whatever multi-section shear flow problem we have will be symmetric, or will it be non-symmetric?
I haven't made the exam, so I don't know yet.
Okay. I hope it is.
It often has at least one plane of symmetry, yeah. Most of the time. I haven't made it yet, so I don't know. I do know in the lecture sheets we go downwards, so but just keep in mind when you see the negative number popping up in the lecture sheets, we go down, but in this case we go up. But the value itself remains the same. So now we can do, basically if you do 6.5, you can add 6.5 to it, but then you will get 0 anyways, but that's what we also got from symmetry, so we're not interested in doing that. So we're gonna do QB 2.5, same thing, negative 2.08, 10 to the minus 4, and then this boom area, which is 1936, like this, 1936, multiplied by 203, and then this must be negative as well, because we are under the negative region of the y-axis. If we do this correctly, we get 81.7 Newton per millimeter. And lastly, we do 3.4 of QB 3.4, which is again negative 2.08, 10 to minus 4, multiplied by 645, multiplied by 3.4 is 101, so negative 101. And that gives us 13.6. Perfect. So we have now determined all the open shear flow sections. Next is determining the correction shear flow, so we can actually solve for the actual shear flow problem. So now we're gonna focus on this part. So what's that part? So basically what we do is we say, well, okay, we have an open section, but we didn't have an open section. So we add a correction shear flow and we can draw that in. Let's use red, because then we can draw our arrows a bit, and we assume to go in a certain direction. That direction is up to you. The only thing that would affect is at the end of the day, if it's either positive or negative, and then we have to check about the signs. So technically, if we draw like this, internally the shear flow goes like this. The correction shear flow, that is. And let's call that QS01, and this one is QS02. So normally what we did is you come up with moment equivalent study or equation, and you would basically have one equation, one unknown. The downside in this case, that will not do it, because now you have basically two unknowns and one equation. So you have to come up with a second equation in order to solve it. And that second equation is, again, because we have multi-section, so every time basically you have a multi-section problem, you should think of the rate of twist. So in this case, we use the rate of twist being equal in cell 1 and cell 2. So the rate of twist was d theta dz, and cell 1 is equal to the rate of twist in cell 2. And this is always valid in a multi-section. So what this does is gives us an additional equation together with our equation for the moment equivalent study. We can basically solve it. So we can do that. We do d theta dz for 1. So we define both equations, and that was 1 over 2 times the area, so that's A1, multiplied by G, and the integral is ds over t. Right? Yeah. 3 ds over t, of course, multiplied by Q. So in most of our previous examples, t was always a constant. So we could basically take that out of the equation or out of the integral, and then we had basically q times s, which was the segment of the where the shear flow acts upon. But in this case, the t is basically different. So what you can do is, and that's totally fine, you can write it as the following. You can just ignore it. So you can area 1, and then you say Q1, say for example, this 1/6, so this is QB, we get 1/6 multiplied by segment 1/6, so that's wall length 1/6, that's 254 over the length 1.625, and you can do that like that. So you basically just because if you evaluate this integral, that becomes s over t, right? Where s is the segment of each, the segment of which the shear flow travels over. And you can basically write down for every part, and we can do that actually. So plus, let's do this cell only, so we get 225 up, so we get QB 25 goes up, so that's 406 over 2.032 plus, and then we have to basically add all the correction shear flows. In this case, let's see, we assumed, wait. Does this make sense? Now we assumed, let me see. Yeah, okay. So I made a mistake. So you cannot just assume positive upwards. You have to assume counterclockwise side positive or clockwise positive. So in this case, one of them is counterclockwise, the other one is clockwise. So these two are not both of them positive. So basically, we have to assume something being positive. Let's assume that counterclockwise is positive. So 6,1 is actually a negative number. So it's going negative, okay? Does that make sense? Saw a head shake, so that's no. So let's redraw that. So we have only focusing on cell 1, okay? So we have determined that this is QB61, QB61, because we go from 1 to 6. And here we have node 2 to node 5, and that's QB25, indicating that we go from 2 to 5. And then we defined the correction shear flow to be counterclockwise. So the correction shear flow goes like this, right? Now what we say is we assume that counterclockwise is positive. So if counterclockwise is positive, then this shear flow going upwards will have a negative association. Because you have to think about it, the QB25 going to try to twist and rotate our section counterclockwise, which was positive, and QB61 tries to rotate it clockwise. So therefore, QB61 needs to be a negative value.
Isn't that 1/6 though? Could be 1/6.
Wait, 1/6. Yeah. Yeah, but it's negative because that one is, here we calculated 1/6 upwards and we get a 32 value, but what it does, it adds clockwise rotation, and we assume then counterclockwise to be positive. Okay. And for the correction shear flow, because they all go in the same direction, we can just assume that the correction shear flow, oh, let's continue here, QS01, everything is positive, and then we just add the lengths of each wall. So we do 254 over 1.625 plus 406 divided by 2.32 plus, so there's those two walls, 5, 6, and 1, 2. That's both of them are the same, so we can do 647 over 0.915 plus 647 0.195. And we're still not done yet, actually.
Does it matter at all that the cuts we made in 1, 2 are 0? Like, would that not make those shear flows in this equation 0 as well? As far as QS?
So we never took Q1, 2 into account because that's 0. But this is the correction shear flow.
Okay.
So the correction shear flow, once you basically drew in the correction shear flow, now it's again a closed section. So now it's again basically closed. That's the addition what the correction shear flow does. Yes.
So, let's say we don't cut it from 1 to 2, we cut the sections at the line where it's dotted. So,
Yeah.
Will it make like 160? I mean,
So if you cut it here
yeah.
and there, then 1, 6 will be 0 and 3, 4 will be 0. And what you have done is you basically have to calculate 5, 6, 4, 5, and then you add those two together. Then you calculate 2, 5,
So what's
and
the-
then you still have to calculate. Yeah, it becomes slightly different.
Alright, so so the value we're getting of QB16, that's 32.8, what's gonna happen with that? Because it's 0 now.
Yeah, but now you have 5, 6 non-zero. Here we never did 5, 6. 5, 6. So QB, say 6, 5 is equal to QB 1, 2 is equal to 0. Well, we also know that QB 5, 1 is equal to QB 2, 3 is equal to 0. So this is basically your initial condition based on your cut. So your initial condition changes, of course, then this also will change. And the last segment that acts upon shear and cell 1 is actually the correction shear flow of cell 2, which goes downwards, because that one also drawn counterclockwise. So because it goes downwards, let's see, you try to add a correction, all this creates an counterclockwise correction shear rotation. This creates a clockwise rotation, so this one is negative again. So you negative QS2 multiplied, this is all in brackets, multiplied by 2.5, so that's 406, which is 203. Yeah, it's 406, sorry, over 2.032.
Is that a division sign or are you just?
That's not a division sign, it's just separation.
So, just like a quick recap, why did we add all the lengths and their thicknesses for QSO1?
Because QS1 is a constant. It's a constant shear flow. So the value of the correction shear flow in cell 2, 5, 5, 6, 6, 1, and 1, 2 is the same. So we could have added, so we can, basically we evaluated this and we notice that this is a constant, so we can just multiply this by all the different numbers.
Okay, so since I guess the length and the thickness of the sections aren't changing, and since the QS is constant, it's having the same effect the entire time throughout the whole integral. So that's what we have.
Yeah.
Okay.
Yeah, because here we have the thickness is taken into account. We do 245 divided by the thickness of that segment. Length of that segment divided by the corresponding thickness. So the point I want to go to is, you can do it that way, or you can do it a slightly different way, and say, it's tomatoes. Basically, it comes down to that. But you can add, say, okay, well, I find it annoying to write out divided by the thicknesses like this. What I do is I introduce a new variable called that delta. I say delta 1/6 is equal to the segment length of 1/6 divided by its thickness. So that's equal to 2.254 over 1.625, which is that number, and then you continue using that number. In some cases, Maxon uses this, so just keep in mind. But it really doesn't matter, because now instead of a fraction, you have a slightly odd number. Yeah, but at the end of the day, it's all the same. Yeah, because then you get, let me see, segment 1/6, you get 153.56.3. So instead of writing this, you would have written down 156.3. Yes.
If we'd only had one of these sections, and like say like section 2 wasn't a part of the question, would it be entirely the same up until QSO2? Like would we still have that QSO1 factor?
Yes and no. Technically, if you don't have a multi-section, they don't do this because it's no longer needed.
Okay.
Because we do this to come up with an additional equation that we can now use in our moment equivalence study to solve that problem.
So it would be there, but we don't need it.
Yeah, so you can calculate the rate of twist of that segment, but you would not need it in the calculations to solve the problem. Say, if I would have said calculate the rate of twist of that segment, then yes. Okay. So we do the same thing for the other segment as well. So d theta dz of 2. Let's do that a bit quicker this time. So 1 over 2 times the area of 2. The shear modulus is the same. And then we get, again, we assume counterclockwise positive. So in this case, 4 is positive, 2,5 is negative. So we get negative QB 2,5. So 406.2023 plus segment QB 34 multiplied by 202 over 1.226. And then we add all the correction shear flows, so that's plus QS02. And that is all the segments. So we get, let me see, 1.6 we don't need, 2.5 we need. So that's 406 over 2.032 plus, let me see, 34, so that's 202 over 1.226 plus, now we get 2, 3, and 4, 5, so that's 775 over 0.559, 775, 0.559, and then at the end we have, again on this cell, we have the segment on this section, we have correction shear flow 2.5 going up, so that tries again to create a clockwise rate of twist, so that's negative. So we get QS025 or QS01, 01, correction, and that's on segment 2.5, so that's 406 over 2.032. And that's your shear flow, or those are your rate of twist. And then you basically have to set them equal to each other. And that's the next thing we'll do. I'll actually rotate it a bit so people at home can see, and I don't have to rewrite it. Okay, I'm gonna rotate back. I didn't notice, so I was off the board a bit. Where's my mouse? So what we can do is we can simplify everything. Yeah. Let's get rid of this. That as Z1. What we get is 2 times 2, 3, 2. And then we get 1770.3 QS01 plus 90 or minus 199.8 QS02 plus 11197. Got lucky.
What was the 23200 vector come from? The A1?
Oh, so the areas were given in the, I assume that those are given in the problem. So I have to double check again with the problem. I don't have my lecture workouts with me, so yeah, the areas are given in the problem. So A1 and A2 were given.
Oh, yes. Okay.
So, and then again, where these numbers come from, yeah, should have wrote it down. Let me write the second one here. The theta dz2 is 1 over 2 times, let me see, 258.00 G. So that's basically the area that's given in the problem. G remains a constant, and then the remainder of these numbers come from the fact that QB25 is known, QB34 is known. So you can basically get these two numbers in, and you can get a numerical number for it. And then you can add all this and that as well. So now you have basically only two variables that are QS01 and QS02.
What's that second? Well, I guess it's the coefficient of QS02.
Yeah, so this one is a coefficient of QS02 is negative 199.8 QS02. So 1770 QS01 minus 200 QS02 plus almost 11,150 almost, because this is 47. Oh, it's 97 actually. 97 the total value. And we can do the same for that as well. So we get here negative 199.8 QS01 plus 33,138.2 QS02 plus in this case negative 14,000 71.5.
Is it any coincidence that the QSO2 value is the same as the QSO1 value in the different phase?
No, it's not a coincidence because they act on the same wall.
Okay, that makes sense.
So what we can do is we can equate these two together, and then we can basically come up with a value for QS01 as a function of QS02. And we need that because for the next step is what we want to solve there is we want to set up a moment equivalent study. And if we do that, what we had to do is we had our shear force on one side multiplied by the location where the moment arm basically is equal to all the shear flows and their equivalent moment arms, right? So where's the best location to do a moment equivalent study around in this location?
Middle of 2.5.
Yeah, that would be a good location, yeah. Because we have basically 2.5 going around it, and let's see, yeah, 2.5 going around. Let's see if there's any better location. No, not really. No. No, there's no better location than that. So we can do the moment equivalent study around 2.5. The only thing that cancels out is basically QB25 and the shear force. So in this case, because we don't have any moment arm, this part is 0. So the left-hand side is equal to 0. That simplifies a bit. We don't have to deal with QB25. We have to deal with QB16 multiplied by the moment arm. That's 635. Let's also make sure that we do the signs correctly. Let's again assume counterclockwise positive. So this goes clockwise, so that's a negative number. This one's counterclockwise, so that's a positive number. So Q plus QB 34 multiplied by its arm, that's 763. And then what we have is, in this case, the area, 2 times the enclosed area of QS01. So that's a plus. Plus another, I'm gonna write it here, plus 2 times the enclosed area of QS02.
And we're doing this, the 2 times the enclosed area because it's centered around the axis.
No, that's a part of the equation, but here we're missing something actually, because we're looking for a moment, so we have to multiply the shear flow with its length to get a shear force, and then we multiply by the arm. So here we have to basically also multiply by 1.6. 1.6 was 254. So this basically becomes minus QB16 multiplied by 254 multiplied by its arm. This becomes QB34 multiplied by this. That was 202, right? Yeah. Multiplied by its arm. And then these two correction shear flows. So where this 2 comes from, if you recall, our equation, we said basically a constant shear flow creates we're looking for an equivalent moment, right? Around a certain point. And from torsion, we had that basically torsion would create 2 times the enclosed area multiplied by the shear flow. That's basically where it comes from. Because the the correction shear flow is a constant, we can use the same principle. So we say a torsion creates a constant shear flow, but a constant shear flow creates an equivalent torsion is nothing more than an in-plane moment which is equal to 2 times the enclosed area times the shear flow. Okay.
Could you explain the negative sign of QE16? I think both should be positive because both are counterclockwise.
No. We define QB16 to go positive upwards. So if you take a moment around this point, that's counterclockwise. No, that's clockwise, and this one is counterclockwise.
Okay, so we're taking the signs that we initially calculated, not the corrected ones.
Yeah. So if you would correct this, then it would be a QB61. But then this number would be a negative, so it's already incorporated. So let me step back. So if you remember the 3 steps, we made a cut, we solved the correction shear flow, and the third step is actually setting up this equation for moment equivalence study, right? In order to find the correction shear flows. But we realize now that we have 2 unknowns and 1 equation. So that's the reason why we need the rate of twist, set this equal to each other, because this gives us an additional equation. Now we have basically 2 equations and 2 unknowns, and now we can solve for both unknowns. So we use the rate of twist equation to come up with a value that says QS01 is equal to X QS02. Then we can plug this relationship into here. We can solve for QS02, and then we can back substitute to solve for QS01. And then we have solved the problem.
And really, the rate of twist equations were the first relationship we had between QS.
Yeah, so I should have started with this one. So yeah, so if we do again our steps for solving a multi-section close, so multi-section shear flow. So step 1 is the cuts. So multiple cuts. Step 2 is solving open section shear flow. That's QBs. Then we have to find the correction shear flow. So close it and find QS0, the correction shear flows. QS01, 02, 03, 04, depending on how many sections you have. To find this correction shear flow, we have that moment equivalence study, or moment equivalence equation. So the moment equation. That's stated on one hand side we had the SY times psi, and on the right hand side we had our shear flows multiplied by the arm multiplied by ds. The segment is acting on plus 2 times the enclosed area for QS0. So because this produces more unknowns than equations, we need the rate of twist, d theta dz of 1 of 2 is equal to d theta dz of 1. And if you have 3 sections, then you have a d theta dz of 3 is equal to d theta dz of 2, and if you have 4, then 4 is equal to 3, blah blah blah. So what these rate of twist equations do, so this gives you a number of x equations to solve the moment equivalence equation. Because now we look at it, we have 2 equations, 1 unknown, 1 equations, 2 unknowns. We add this to it, becomes 2 equations, 2 unknowns, and we can solve for it. So let's redraw this figure and I will give you the solutions. So if you do it correctly, QS01, QS01, and QS02, that will be equal to 7.2, so negative 1.1, and negative of plus 7.2 Newton millimeter. So now we go back to this equation, to this board, or to this figure. So what we do is we basically add in all the correction shear flows. So here we add, so this is negative 1.1. So basically it means it goes opposite direction. So let's draw the positive direction. So this goes like this. So this is 1.1, 1.1, 1.1, 1.1. This was 32.8, 32.8. This one was upwards 81.1. So let's draw it here, 81.7. This was 7.2. So that's already in the correct format. 7.2, 7.2. And this one was 13.6. So our final part would look like something like this. So we have 32.8 upwards in the same direction, so you can add them together. So this becomes 33.9. I'm dropping the units for now. This is 1.1 in that direction, 1.1. Because it was 0, since we made a cut. This one is to the left, 7.2. This one is to the right, 7.2. This one is to the left, 1.1. And here we have basically 81.7 minus 7.2 minus 1.1. So we get 80.6 minus 7. So 73 is 72.8 downwards. 72.8. Oh, and here we have 13.6 plus 7.2 because they act both in the upwards direction. So you get 20.8. So this will be your final shear flow.
Would it be 72.8 upwards?
Yes, it will be upwards.
So you're getting these values from which equation exactly?
So there are multiple equations. So when we made a cut, we get it from our standard equation of shear flow. That's negative Sy over Ixx multiplied by the B times the Y distance. But because we made a cut, we have to introduce a correction shear flow. That's basically to overcome the side effects of the cut. So the correction shear flow is found by a moment equivalent study, where you basically say the moment caused by the shear force must be counteracted by internal moments caused by the shear flows. So that gives you an equation that has QS01 in it. And if it's a multi-cell, then you have QS0S1 in it, QS02, 03, 04, 05, depending on how many cells you have. So you have one equation with more than one unknowns. So now you have to come up with additional equations to help solve that first equation you have. So then there's where the rate of twist comes into play. So for each cell, you have the rate of twist set into to its equivalent adjacent cell. So cell 1 is equal to cell 2 is equal to cell 3, etc. So what you can do with this additional equation is come up with a value for QS01 is equal to X value of QS02. right? You can set them to equal to each other, and then you can substitute, and you can come up with an equation. QS01 is 5QS02, for example. Okay? Once you have that, you can back substitute that into this equation, and now you have not one equation, two unknowns, you have one equation, one unknown. So you can solve for that one unknown. And the second unknown will be solved by this relationship. Say, for example, here you get QS01 is 5. If QS01 is 5 QS02, that means QS02 is 1 over 5 QS01. So this becomes 1. Okay? Yes.
Can you explain the 20.8 on the far right side? Is that just QB34 plus 7.2?
Yeah.
Okay, and it's going up.
Yeah, it's going up. Because if you remember correctly, we assumed in the beginning that both correction shear flows would go counterclockwise. So we drew them all upwards, right? And here we said, oh, QS02 is a positive number. So that means that, look, how we drew QS02 is correct. Here we got a negative number. So that means that how we drew QS01 being counterclockwise was incorrect. So it's actually clockwise. That's the reason why we flipped the arrows and we pointed out downwards.
Okay, and the 72.8, that's the just 2.5 minus 7.2 and 1.1?
Yeah, because those two go downwards and this goes upwards. And that's how you come up with your final solution. Any questions?
Would you prefer the final solution in picture form or in like a list of cues?
It doesn't matter.
Okay.
I think in the past I've specifically asked for draw it in, and sometimes I just ask to just give it as numbers. It depends on the problem, to be honest. Okay, so that's it for this lecture. So yeah, we have 3 lectures left. I will choose one more additional topic. That will be probably shear and panels and the cutouts. So what happens if you remove one panel, what happens with the shear flow distribution, how you can redistribute that. So we discussed that, and then, like I said, not this weekend, so not the weekend of the 17th and 18th, but the weekend of the 24th, 25th will be the first exam, and the weekend after that, of May 2nd, that's where the second exam will be. Again, 48 hours, starting on Sunday, ending on Tuesday, so you should have plenty of time to do it. Okay, thank you.